Well, hello. Welcome back. This is a lecture on a continuation of the foundation of data science or the mathematics of data science and machine learning. So, in this lecture, we're going to talk about. I think in the previous lecture we talked about Gaussian elimination. In this lecture, we're talking about the possible conclusions by combining multiple truths. Basically, a continuation of Gaussian elimination that we did. So, in order for you to understand this lecture, make sure you already went through the lectures on matrix vector operation, as well as you understand the basics of Gaussian elimination and what we've done so far. Okay, so let's get started. I am Professor Wu. So, we learned Gaussian elimination in the last lecture, right? Basically, you can manipulate a system of equations, and by manipulating them in a smart way into what we call the RREF, we are able to like come up with some kind of conclusion solution for the system of equations. However, a linear system of equations may not it may not always have a nice unique solution we saw last time with and we like once we reach REF, maybe we don't have a solution. In fact, in general, there are three possible cases. The initial case is what we saw last time, is that there is a solution. However, there are cases where no solutions is possible. There's like we have contradictory statements, for example, or we have maybe infinite solutions. So there are many ways, many solutions in those cases. So why don't we let's start off by taking out a piece of paper and see if you can try to solve this based on what we learned last class. Okay, pause the video and then we'll move on once you solve this. Okay, so with the solution, well, we remember what we tried to do from last class is that we try to reach this thing called RREF, where the upper triangle and the lower triangle are zero. However, notice that if you simply do one operation, you end up getting a row of zeros. So the diagonal in that element is also zero. Now, that's not really a problem. The only problem is if we convert this statement back into equation, right? Remember, how do we go from here to here? And now let's see, we try to go from here and back to like these equations. It would essentially be we multiply x1 and x2 back into the system of equations. And after we multiply, and notice how this is 1x1 plus 2x2, right? Equal to 1. And then the second statement is 0x1, 0x2, which results in this. Well, if you look at this carefully, notice that we have a problem. 0 times x1 and 0 times x2. So it's saying that 0 is equal to -1, which is contradictory. Right? So this contradicts truth because this is not possible. You can't have 0 equal to -1, right? They can't equal to each other. And whenever there's a contradiction in the statement, it basically tells you that in this like system of equations, it's not even possible that they're all true. Something is contradicting something else. And specifically, this equation is contradicting this equation. And in those cases, you don't have a solution. Okay? You don't have a solution. And that's the case where there isn't a solution and that it is impossible. So this is possible. And this arises whenever you do try to achieve the REF and you get a row of zeros equal to some number, right? You have 0 cannot equal to a number, so there's a contradiction. And this is how it normally manifests itself. And you need to keep that in mind when you see a linear system of equations and you're trying to reach the RREF, and then you see something like this. And you now know how to deal with it. Essentially, that's the case where there are no possible solutions. Let's try this again. In this time, there's also a contradiction, I think. Is there a contradiction? Yes. So there's still a contradiction. So pause the video, give this a try. To think about what we did so far, and I'm going to move on. Hopefully, you paused the video and solved this already. Well, in this particular instance, if you perform this action, notice that you also create a contradiction where you have a bunch of zeros and then you have a one, right? If you have a bunch of zeros and you have a zero here, that's fine. That's not a contradiction because zero equal to zero is not a contradiction. However, if you have zero equal to some number here, then we have a problem. Right. So in this particular case is another example where a solution doesn't exist because the equations are contradictory with each other. Okay. All right. So let's move on in part two. And this part two is called Anatomy of Matrices and their names. Specifically, we're going to learn these two things in the matrix. So in the last class, we talked about how we can go from a matrix, right, augment a matrix, and we can reduce it so that you have the diagonal and the lower part is zero. And then we can reduce it farther so you have the diagonal elements where the upper and the lower. And this lower part is called the REF. If you achieve REF, it's pretty useful. You can use it already. But ideally, you want to achieve RREF. So this is called the reduce row echelon form. Echelon form. Right? And this one is the reduced row echelon form, and this one is the row echelon form. Okay? Anyways, so the point is, ideally, you want to reach a point where you got zeros on both sides. But reaching REF is actually useful in some ways. For example, like it allows us to identify if a variable, so is x1, x2, x3, x4, is either a leading variable or a free variable. Now, there's reasons why we want to identify leading or free variable. So in this particular case, if we convert this equation, right, into the matrix vector multiplication format, so you can see this is 1, right? This is 1, 1, 0, 0. Notice 1, 1, 0, 0. Okay? In this particular case, there is obviously a contradiction because it's saying that 0 is equal to 3, which it can't be. 0 equals to 2. So you got like a lot of contradictions, so that can't be. But what I want to point out is that once you reach this form, which is the REO form, the upper triangle is still not 0. This is just reduced echelon form. Well, it allows you to essentially pick out leading and free variables. What you do is basically you look at each row and look at the first non-zero value, which the first non-zero value corresponds to x1, right? It's x1. And that is the leading. All right. You look at the next row, the next non-zero value is x2. That's also leading. And then there's nothing here, right? Everything is 0. So none of these are leading. Anything that is not leading must be a free. So this implies that x3 is free, x4 is free. So I just went through like a kind of confusing way of how we can identify out of x1, x3, x2, x3, x4, which one are leading variables and which one are free variables. Okay, I wanna do this one more time because there's a little bit of stuff you would need to kind of remember. Basically, once you reach the reduced echelon form, you can then start identifying these. And the reason why you want to identify this is because it tells you the type of solutions you have. Okay, and I'll show you how that works. But first, you need to know how to identify them. So you just basically look at the first non-zero values. That's basically it, and those are the leading. And anything that's not a leading is a free one. Okay, so you can identify leading and free. Okay, I think it might be easier if we look at a couple more examples. So in this particular example, we have x1, x2, x3, x4, right? This is in the REF form. Therefore, it's saying that x1, x2, x3, x4, they're all leading. So these are all leading. And anything that's not leading is a free. But since everything is leading, we don't have any free variables, none. Okay, so that's one example. Let's look at another example. In this example, we see that this is the first one, x1, x2, x3. So x1, x2, x3 are leading variables, and the only one left must be the free. So x4 must be free variable. Okay, let's look at another example. Hopefully you start seeing the pattern. In this case, we have x1, x2, x1, x2, and this one is 1, 2, 3, 4. So this is x4. So these are the leading. And the leftover is x3. So this is the free. So that's how you identify leading and free. Let's first see if you can identify them. Then we can talk about, like, okay, why do we want to identify them, and then how are they used? Okay, so let's see if we can identify them. Here are two matrices. Pause the video and see if you can identify which variables for each one of them are free and which one are leading. Okay. Okay. Pause the video. I'm gonna move on. So over here, notice how we have 1, 2, 3, but there's nothing at 4. Therefore, 1, 2, 3 are leading, and 4 is free. Over here, we have 1, 2, 4. So x1, x2, x4 are leading. X3 and x5 are free. So that's how you identify leading and free variables. So okay, so let's go over why do we call it leading? Well, leading makes sense, right? Because it's the very first one. The very first one. So the leading makes sense. But why do we call it free variable? And why is it important and necessary for us to identify leading and free variables? Well, okay, let's look at this example. And we're going to convert this into an augment matrix. So it was 1, 3, 1, 0, 1, right? 1, 3, 1, 0, 1. So we basically converted into an augmented matrix. And based on our understanding, we know that x1, x2, and x4 are leading. x3 and x5 are free. That's what we know. Well, the reason why they're called free is because in order for us to solve x1, x2, x3, well, we need to know what x3, x5 are. If we don't know what they are, we cannot solve these. So we're free to choose any number. Any number. Right? In these cases, whenever there's a free variable and there are no contradictions, it's saying that we end up having infinite solutions. Infinite solutions. Because we can pick any value of x3 and x5. And once we pick x3 and x5, then we get the solution x1, 2, 3, 4. So by the fact that we can pick any number we want implies that they're infinite solutions. Okay? And you will see why. You'll see why. I think this makes more sense if you actually do an example yourself. So let's look at this. Let's look at this here. And let's say that we know that x3 and x5 are free. So if you pick some value, then we can solve for x1, x2, x4. So let's just pick some value. I'm going to pick x3 is equals to 0, x5. Okay? Let's pick two of them. And your job now is to pull out a piece of paper and essentially identify x1, x2, x4, given that this is known. Okay, this will show you why knowing them is necessary. Okay, pause the video, give this a try, and I'm gonna move on. Okay, hopefully you did the exercise. If you did the exercise, you will see that you have to pick x, what was it, x3 and x5. If you don't pick x3 and x5, there's no way you can solve these. All right, so we are free to choose this. Once we choose this, we lock up the solution for these. All right, so that's kind of the general idea, and we're going to build on top of this. So you need to take a moment, think about free leading variables, and the reason why we need to separate them is because we need to know which variables we must know ahead of time in order to solve the leading variables. All right, so all of these that I've taught you basically leads us to the case where we have infinite solutions. And it makes sense why they're infinite solutions because you can pick any number you want for the free variable. Then you get the solution for the leading variable. So identifying free variable lets us identify the third possible solution, and that is when you have infinite solutions, right? So this is the case of the infinite solution. And okay, the natural question arises: if you have a linear system and this system has infinite solutions, then how do you represent the solution? Okay? Because it depends on what you pick as the free variable, right? You pick one free variable, you're going to get one solution. You pick another free variable, you get another solution. And the answer is the solution is not fixed because there are infinite of them. Instead, the solution depends on what you pick for the free variable, right? So what we end up doing is that the solution is simply a function where you're putting the free variables. And then that will give you the solution for x1, x2, x3, x4. Okay, so you put in the free variable you pick, and then you will say based on this free variable, you will have these kind of solutions, right? And you can put any free variables in. So in this particular example, right, we have a function that looks like this, where we put in a vector like this. We put a vector in here, and we pick x3, in this case x4. So we basically pick the free variables. And then the output, by multiplying this together, the output give us the solution. So notice how this gives us infinite solutions because you can pick any number you want here. So the question is, wait a second, how did you get this? How did you get this function? Right? How did you get this function? And this function is the solution. When you have infinite solutions, you create a function where you can pick any free variable, then you give you one instance of a solution. And the solution looks basically like this. Okay. Well, let's step by step look at an example and see how we got to the solution. So from our previous problem, we had this was a problem we solved, right? So this was the augmented matrix, and this was the system of equations we're trying to solve. We're trying to figure out what x1, x2, x3, x4, x5s are, right? So in this particular case, we know that x1, x2, and x4, x1, x2, x4 are leading. And then x3 and x5 are free. So that's what we know. Free. Okay, so how do we get the solution? Well, once we achieve REF, right, that's the key. First, you got to achieve REF. In this example, I already achieved REF for you. So once we have REF and we have identified leading as well as the free variable, then all we have to do is to set all the leading variables in terms of free variable. Okay, I'll say that again. We will set all the leading variables in terms of free variable. Okay, what do I mean by that? Well, what is x1? All right, let's look at the very first equation for x1. So x1 plus 3x2 plus x3 plus 0 plus x5 is equal to 1. Well, this means that we know what x1 is. x1 must equal to minus 3x2 minus x3 plus x5 minus 1 plus 1. Okay, so we now know what x1 is. However, x1 is not in terms of free variables. x3 and x5, these are free, but x2 is not. Okay, so what is x2 then? What was x2? Well, x2 is here. So let's look at x2. x2 is actually I wrote all these down already. So x2 is basically 2 and then minus x2 minus x3 plus x4, right? So x2 is equal to this. So x2 is its own equation, but it's still using a leading variable, x4. Okay, so what is x4? x4 is pretty easy. x4 is equal to 2x5. Okay, 2x5. All right, so this equation, the leading variable is in terms of free variable only. So now we can plug x4 in here. So now x4, instead of x4, we just replace it with 2x5. So now we have an equation only in terms of the free variable. We do the same thing because x2 here is not a free variable. So we plug x2 in, and then the result is x1 is some combination of x3 and x5. Okay? So let me repeat that. The first step of getting a solution that has infinite solution is to put all the leading variables in terms of only free variables. So this equation has only free variables. So that is step one. Step two, we set all the free variables to itself. So x3 is equal to x3, x5 is equal to x5. Now we have an equation for everything. We know what the equation for x1 is, right? We know x1 because we got it here. We know the equation for x2. We got it from here. We know the equation for x4. We got it from here. And then what is the equation for x3? Well, x3 is just equal to x3. x5 is just equal to x5. Okay? So this right here gives us another system of equations. Right here, we start with a system equation, and it turns out that the solution is also a system of equations. And then we simply rewrite the system of equation this way. So it's saying that this becomes a function where we can pick any x3 and x5. By picking any x3, x5, we multiply it. Now we got a solution to this original system of equations. So that is kind of interesting, right? So this right here is essentially a function where you put a vector in and you get a vector out. Okay, I like this is not easy. Like there are quite a bit of steps you have to memorize. Specifically 3 steps, right? Let me go over this one more time. The very first step is, well, reach the REF, right? And then you need to pick out the leading and the free variables. So that's the first step. And then once you know those, what you want to do is you want to set all the leading variable in terms of free variables. So you got a system of equations. And then you set all the free variables to itself. That's the next step. Then you have equation for everything. You have equation for everything. And you simply now rewrite it this way. Okay? These set of steps, it requires you to practice a couple times to remember, right? It just takes practice to remember. So why don't we just practice? Right here is the is another example. I believe it has infinite solution. Follow the steps we went over. Think about it. It takes time. Think about it and see if you can produce the solution yourself. Pause the video. I'm going to move on. I basically giving you a step-by-step process, right? I'm going to do the reduced row echelon form. If you're confused, you can study this on your own. And it takes a bit of time. Over here as well is the continuation of the solution, and over here is the final solution. Okay, so that's basically the idea. Now, you doing one question is not enough. You will need to do lots and lots of questions in order for you to get this. But hopefully, at this point, you get it. You have an idea. Now, in order for you to solve, in the last lecture, I told you that you can use solve to solve it. However, solve only works in NumPy. It only works if you have a unique solution. It will not work if it's no solution or infinite solution. It will not work for those two cases. It will just crash, in fact. Over here, here's an example. I try to run a solve, and it just crashes. And it's called, this kind of crash is called singular matrix crash. So you're going to get a singular matrix crash, and you know that, okay, there isn't a solution because there's either a contradiction or there's just infinite number of solutions. Now, in order for you to solve this, when you run into this problem, there's an alternative approach. The alternative approach is to use SymPy. Notice how I import a different Python library. In SymPy, you can write the matrix out, right? You can write the matrix, and then all you have to do is to call the RREF. So matrix M, and then you call the RREF, and it gives you the RREF solution. So in this particular case, you see that there is a contradiction, right? Because 0, 0 cannot equal to 1. So this right here is a contradiction. In this other example, there are no contradictions. However, you have free variables. Whenever you have variables without contradiction, implies that you have infinite solution. So you can essentially get the infinite solution from knowing that it's infinite solution or contradiction using SymPy. Okay? All right. The shape of the matrix, just by looking at the shape, then you can kind of whittle down the type of solutions you may see. So if it's a square matrix, then it could be anything. It could be unique, no solution, infinite solution. So it doesn't tell you much if it's a square matrix. However, if it's a tall matrix, oh, it's the same. So square and tall doesn't tell you much. The only one that really tells you is if you have a fat matrix. In fat matrix, then unique solution is out. So it can only be no solution or infinite solution. Now, when we solve a linear system, there's a logic, a geometric logic to the solution, right? So if you think about it, what is this really? Well, it's ultimately just a line. This is the equation of a line, like this. And this is the equation of another line, right? So what happens when we are solving like a linear system of equations is that you're drawing two lines. Right? In this particular example, it's easy. So you're drawing two lines. And then since x and y has to be the same, the solution is the point of intersection. I don't think about it like these are all the possible xy values for one of the equation, and these are all the possible xy values for the second equation. And in order for x and y to be the same, the solution is the location of intersection. So so when you think about finding the solution of a linear system, the geometric meaning is that you have one system and another system, and their answer has to be the same, right? Therefore, it has to be a point where they intersect. So this is the example where there's a unique solution. There's one point of intersection. However, in some cases, if there are no solution, it's because they're parallel. And what that's saying is that they never intersect each other. So it's impossible for intersection. So that's the geometric understanding of why it's possible to not have any solution. And for the case of infinite solution, it's because they overlap each other. It's the same line. If it's the exact same line, then that's an intersection. That's an intersection. So every single point is an intersection. This is easy to see in 2 dimension. In higher dimension, then it's harder to visualize. But the idea is the same. Right? In this particular case, the intersection is right here, right? So you do have an intersection. All right. So let's practice this idea more. Now, I have a bunch of systems, right? And your goal is to identify if it has a unique solution, no solution, or infinite solution. Okay? So pause the video now. You want to make sure you do this and then go over the solutions here. Okay? Right, the final exercise of the day, solving linear systems. Okay, well, 1, 2, 3, 4, 5. You have 5 problems you need to solve, and like at the end of the day, I can just talk and talk and talk. It's not until you do it yourself that you start absorbing this knowledge. So start absorbing, start doing this, and the solutions here and here. I will see you in the next lecture. All right.